Let's discuss how Sir Isaac Newton advanced the understanding of physics in general and gravity in particular, building on the accomplishments of his predecessors. Isaac Newton, one of the greatest names of physics, made major contributions to the discipline. Among them, he created calculus, which is the mathematics of motion. He formulated the three laws of motion, and he devised the theory of universal gravity. These contributions were so significant that in Newton's epitaph, what is written in his tomb, this is Newton's tomb in Westminster Abbey in London, his epitaph was written by the poet Alexander Pope, who said, "Nature and nature's laws lay hid in night. God said, let Newton be, and all was light." Newton himself was more modest. He said that if I could see further, it was only because I stood on the shoulders of giants. So these are the giants that Newton was referring to: Copernicus, Galileo, and Kepler. And to understand the importance of their discoveries, we have to take a step further back and see what existed before them. Let's step back to ancient Greece. Aristotle thought that the universe was composed of four elements: earth, air, water, and fire, and that everything was composed of these four elements in different proportions. And he thought that motion was because these four different elements sought their natural places. The evidence for this is that rain, water, falls from the sky, so its natural place is the earth. Rocks fall when thrown, so their natural place was also the earth. Smoke, air, would rise, and flames, fire, also rise, so their natural motion is up. For stars and the planets, Aristotle couldn't fit these four elements in his idea, but he thought that they were composed of something else. Their motion being so regular, he thought that they cannot be made by the same corruptible and blendable elements. They must be made of something else, a fifth element that he called ether. So for Aristotle, the universe has two very different behaviors. One is sublunar physics, which is the Earth, everything under the orbit of the moon, and superlunar physics, which is everything beyond the orbit of the moon. And very different laws govern the Earth and the heavens. Motions in the heaven occur in perfect geometry. Everything goes in circles. The Earth is immobile in the center of the universe. Using this idea for the motion of the planets, Ptolemy explained it mathematically how the planets moved. Ptolemy was a great astronomer, but with the wrong theory. He described this geocentric model mathematically nearly to perfection and was thus able to correctly predict the position of the planets. There was one thing, though, that he had to explain, which is the retrograde motion of the planets. If the orbits are always circle, you would imagine that the planets would just continue in a line orbiting the Earth. But what is seen in the night sky is this. You see that a planet, in this case here Mars, goes in its trajectory, stops, reverses the motion, stops again, and goes back to its original trajectory. This reversal is called retrograde motion, and it was not immediate how to explain. If all the motion in the ether is supposed to be uniform and circular, what is going on? An ingenious idea of Ptolemy was to use epicycles. The planet is not actually going around the Earth, it is going around a point, and this point is going around the Earth. That was the idea of Ptolemy. So he uses the two circles, not just one. The planet itself executes an orbit, which is the epicycle around the point, and this point executes an orbit, which is the different around the Earth. With these two circles, then Ptolemy could explain the retrograde motion. It's showing here what the trajectory would look like if you had this planet going around the epicycle and the epicycle going around the Earth. This is the trajectory seen against the background of distant stars. You can explain the retrograde motion in this way. With this model, Ptolemy summed up Greek thoughts on astronomy with a round Earth around the center, surrounded by spheres where the planets are moving. And with that, he could predict the motions and the eclipses fairly well. In fact, this is such a good model that is used today in planetaria all around the world to simulate planetary motion. Just the gears and motors substitute the epicycles. But we know that it's actually the sun that is in the center, and the Earth is just a planet that is going around the sun. This was explained by Nicolaus Copernicus. the Polish astronomer. If you go to Poland, you're going to see here that he features in banknotes. So this is the explanation of retrograde motion in the Copernican system. You have simply that the Earth is going faster than Mars. And from our point of view, then, this is the line of sight connecting Earth and Mars. So this is what we see against the background of distant stars. When the Earth overtakes Mars, we start to see the retrogradation. So next comes Galileo. Galileo explained that the Earth pulls all bodies with the same force. And that is the idea of gravity. So legend tells that he made an experiment in the inclined tower of Pisa where he dropped the two spheres, two balls, with different masses. And the Aristotelian idea was that bodies of different mass would fall with different speeds. And that's somewhat backed by evidence. If you drop a hammer and if you drop a feather, they fall with different speeds. It wasn't clear to Aristotle that the feather is falling with another speed because it has resistance from the air. The fact that a feather and a hammer should fall with the same speed is actually very counterintuitive. This experiment with the hammer and the feather was actually done on the moon by astronauts.
Well, in my left hand, I have a feather. In my right hand, a hammer. I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Mr. Galileo was correct in his findings.
This is probably a legend that Galileo dropped the balls from the Tower of Pisa. In fact, what he did was what we call nowadays a thought experiment. Imagine that you have two spheres, 1 and 2, that have different masses, with M1 being less than M2. Now, if the heavier sphere were to fall faster, then if you attach them together, sphere 1 would slow down sphere 2. So the resulting velocity will be between the velocities of V2 and V1 that the spheres would attain if they were released individually. That's the situation that is sketched here on the left-hand side. Now, you can imagine also that the two spheres attached actually result in a single object of mass equal to m1 plus m2. Now, in this case, if the velocity is bigger, if the velocity depends on the mass, then the whole ensemble should attain a velocity that is bigger than either v2 or v1. So the only way to reconcile the paradox is to have the velocity equal to v2 and v1. So all bodies follow the same velocity independent of their masses, and they are thus subject to the same acceleration. Galileo was also the first to use the telescope, which was then a toy, to look at the night sky. He made many discoveries. Among them, he showed that Venus orbited the Sun and not the Earth. He did that by observing the phases of Venus. Venus is an inner planet, it's orbiting the Sun. So viewed from Earth, you would see different fractions of Venus being illuminated by the Sun. You would see the phases. Venus would have, in the situation, would be a crescent. Here, Venus would be half illuminated. When Venus is on the other side of its orbit, you see a full phase, and then it's going to start to wane. And then again, you see the gibbous phase, the half phase, a crescent, and then a new. You would have the same phases as the moon. This is what is illustrated here. This is what you should see if Venus orbited the Sun. So 1 to 2 to 3, you would be waxing, and 4 to 5 to 6, you would be waning. Now, if Venus orbited the Earth in an epicycle, the side that is illuminated by the Sun would be always towards the Sun, and we would never see a full phase of Venus. These are the phases that should be seen in these different positions. Galileo showed that the phases that are seen are precisely the ones that are expected if Venus is orbiting the Sun. Back then, it was common that scientists would write it to their colleagues using anagrams to hide their discoveries, but still have a fingerprint of primacy. Say that someone else had discovered it, they could point it to a letter that they sent and unscrabble the anagram and show that they actually knew that before. Galileo sent this anagram here. Of course, they wrote in Latin. When the anagram is unscrabbled, what is revealed is this: the mother of love, that means Venus, imitates the shape of Cynthia, the moon. Another discovery that Galileo did refers to Jupiter. When Galileo first pointed the telescope to Jupiter, he saw 4 objects orbiting Jupiter. These are nowadays called the 4 Galilean satellites of Jupiter. That was the first time that something was seen orbiting another body than the Earth. This is a time sequence from the New Horizons spacecraft as it was in flight to Pluto, approaching Jupiter, clearly seeing the motion of the moons around Jupiter. You can see these moons with a backyard telescope, and if you observe night after night, you can follow the motion of the moons around Jupiter. Galileo did that. This is a page of Galileo's book Sidereus Nuncius. It was showing here observations done in different days and the position of the moons, a time on one side and a time at another side of Jupiter. Next, Kepler. Kepler formulates what we call now the 3 laws of planetary motion. The first 2 laws he derived by using observations of the motion of Mars. By studying the orbit of Mars, he tried to fit a circular orbit to Mars, and he realized that he couldn't. He tried the different shapes until he realized that the shape that fit the orbit was an ellipse. So that was the first orbit. The orbit of every planet is an ellipse with the sun in one of the 2 foci. So here's the sun in one of the foci. The other focus is empty. You have 2 different orbits, 2 completely different orbits. Both of them have a focus on the sun. The second law is that a line joining a planet and the sun, which is this line here, sweeps out equal areas during equal intervals of time. The time that the planet takes to go from this position to this position in its orbit, the line connecting the planet and the sun swept this area here, A1. When the planet is on this part of the orbit, the same time that it took for the planet to go from this position to this position, here is highlighted at this segment of the orbit that's done at the same time. This area A2 is equal to this area A1. As you see, there are 2 laws here. There's missing the third law. The third law Kepler found 10 years later and has to do with motions of different bodies. He found that the square of the period of a planet is proportional to the cube of the semi-major axis of the orbit. So let's understand how Kepler got to this. So again, these are the moons of Jupiter orbiting around it. Galileo drew here the position of the moons at different dates. If we space these observations regularly, spaced by 12 hours, this is what you would see. It's clear here that you can follow the orbit of the outermost moon, Callisto, and you can make out also here the orbit of the third moon, Ganymede. So from that, you can tell the maximum distance to Jupiter and the period of the orbit, the time that it takes to go back to the same configuration. The other 2 moons are harder to find, but you can still do that. And this is what you find then. So this is the orbit of the outermost moon, Callisto. This is Ganymede. The other 2 moons, this is Europa, and the inner one, Io. You can tell from this the distance and the period of each of the 4 moons. And if you plot them, this is what you get. On the horizontal axis, that's the distance from Jupiter in units of the orbit of Io. And on the vertical axis is the orbital period in days. You can connect these 4 points, the 4 moons, with a line that is proportional to the power of 1.5 of their distance to Jupiter. So the power of 1.5 is a non-integer number. If you square it, then you'd have the square of the period and then the cube of the distance. So the square of the orbital period is proportional to the cube of the distance. And Kepler showed that the same thing applies to the planets. This is the distance from the planets to the sun. in units of the Earth's orbit, and the period in years that it takes the planets to go around the sun. Again, they beautifully follow also this relation that the period is proportional to the distance to the power of 1.5. So that is Kepler's third law. The square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit. And here lies what Kepler found and Newton also found to be a profound truth about how bodies move through gravity. The planets are not moving with different periods because their orbits are larger. If that was the case, the period would be linear with the distance. But it doesn't go linearly. It goes with the power of 1.5. So planets are not like racers that they all go with the same speed. On larger orbit, they move slower. By Kepler's third law, you can conclude that planets that are inside are moving faster. So stuff that is close in moves fast, and stuff that is far out is moving slow. Kepler then hypothesized that if that is the case, if when stuff is close to the sun, it moves fast, and when stuff is far from the sun, it moves slow, that means that what keeps the planets in motion is something that emanates from the sun and dilutes with distance. And that is very similar to how light behaves. You have here the sun, and imagine that you have two different spheres here. So the same amount of light expanding spherically outwards crosses progressively larger areas. Mathematically, you can calculate that it leads to an inverse square law. As the distance increases, the same energy spreads for a larger area. Area goes with the square of the distance. For the energy to be the same, then the illumination has to decrease with the square of the distance. Now, if gravity behaves in the same way, it has to decrease with the square of the distance. That was one of the insights of Isaac Newton that led to what is called then the inverse square law for gravity. Now, Newton also realized something else. He realized that the same force that is giving gravity on the surface of the Earth is what is keeping the moon in orbit. For that, he did a mathematical calculation. He knew that if the moon is going around the Earth, it is subject to a centripetal acceleration. Scientists before Newton had established that the expression of the centripetal acceleration, that is called A, is the square of the velocity that the body is orbiting, over the distance, the radius of the orbit. So Newton calculated the value of the centripetal acceleration for the moon. The moon is distant about 238,900 miles from Earth. So that's what you put here as d. For the velocity of the moon would be the circumference that it has to go. So that's 2 pi times the radius of the orbit over the period. So the period of the moon around the Earth is 28 days. The velocity, you do this calculation and you find about 1 kilometer per second, which is about 2,288 miles per hour. You put this velocity and this distance in this formula, and you find an acceleration of about 2.7 times 10 to the minus 3 meters per second squared. So that's the centripetal acceleration that is keeping the moon in orbit. If gravity was responsible for keeping the moon in orbit, you would find that the value of the acceleration of gravity from the Earth to the moon would give you the same value. That's what Newton did. After finding that gravity falls with the square of the distance, this would be the acceleration of gravity, g times m over d squared. Now, m here is the mass of the Earth, g is the gravitational constant. The mass of the Earth is 6 times 10 to the 24 kilograms. G is 6.67 times 10 to the minus 11 meter cube per kilogram per second squared. If you replace here d by the radius of the Earth, you find the acceleration on 9.8 meters per second squared, which is the acceleration on the surface of the Earth that we all experience. Now, if you put instead the distance to the moon, 238,900 miles, what you find is that the acceleration of gravity at the distance of the moon is about 2.7 times 10 to the minus 3 meters per second squared, which is exactly the centripetal acceleration that Newton had computed before. So Newton's conclusion was that gravity is what keeps the moon in orbit. Newton wrote about this. At the same year, 1665, I began to think of gravity from Kepler's rule of the periodical times of the planets being a sesquialterate proportion. So sesquialterate is a word that we don't use nowadays. It only means 1.5. So the rule of the periodical times of the planets, so the orbit, the period of the planets being in a 1.5 proportion of their distances from the center of their orbits, I deduced that the forces which keep the planets in their orbs must be reciprocally as the squares of their distances from the centers about which they revolve, and thereby compared the force requisite to keep the moon in her orbit with the force of gravity at the surface of the Earth, and found the answer pretty nearly. So Newton's explanation that unified the physics of the Earth and the physics of the heaven is that the moon is constantly falling, but constantly missing the ground. If you had a very tall mountain and you shot a projectile, if you gave too little speed, you would fall towards the Earth. If you gave it a little bit more speed, you would go a little bit further. That's what we usually experience. But if you gave just enough speed, it would orbit the Earth. You would go around the Earth and then come back to hit you in the back. For Newton, that is what the moon does. The moon is going around the Earth, is falling towards the Earth, but constantly missing the ground. And then if you gave an even further speed, you would make the projectile go in an elliptical orbit. You'd go a little bit further than the orbit C, and you would come back to the same point. That is an elliptical orbit. So he explains why Kepler found elliptical orbits. It has a little bit more energy than a circular velocity. And if you give even further speed, you would escape and not come back. This is how Newton unified the physics of the Earth and the physics of the heavens under what he called the universal law of gravitation.